Hello and welcome back to Math Class in Session. Today, applications of calculus to problems involving exponential functions. And they'll be mostly maximum and minimum applications. It's a fairly tough area of calculus, so you need to know how to pause the video. To do that, you hit the space bar if you're using a PC. To advance the video a few seconds, you just hit the right arrow, and to go back a few seconds, you hit the left arrow. And if you're using a tablet, double tap the right part of the screen to move ahead, and double tap the left part of the screen to go back. So take a deep breath and relax, and let's do some max-min word problems with calculus. Page 245, number 2. Use the algorithm to find extreme values to determine the absolute maximum and minimum values of the functions. And they give a couple of examples here. Here's a function f of x equals e to the negative x, subtract e to the negative 3x over the domain from 0 to 10. Now the algorithm says evaluate the y value at the critical points and the boundaries. Well, here are the boundaries, 0 and 10, so what we need are the critical points. To find those, we set the derivative equal to 0, so we'll have to differentiate. E to the negative x primed is negative e to the negative x, and this is going to be negative e to the negative 3x differentiated. We make a copy of it times the derivative of the exponent. And I just tidied that up a bit right here. Negative times a negative is a positive. Now we'll set this derivative equal to 0, which I do here. And also, I've factored out e to the negative x because I see it here and I see it in both of these two terms, and e to the negative x. So I took it out. And I put in brackets the result of dividing it out. Checking my factoring, e to the negative x times negative 1 is negative e to the x to the negative x. That looks good. And e to the negative x times 3e to the negative 2x is plus 3e to the negative 3x. And that looks good too. Don't forget, when you multiply these powers of the same base, keep the base and add the exponents. So I just checked my factoring. Now rearranging this second factor, because it looks weird with the minus 1 out front. It looks weird with the minus 1 out front, at least it does to me. So I rearrange it that way. Now to find the critical points, we'll set the factors here equal to 0. Now e to the negative x is never 0. I don't care what exponent you put on e, you can't turn it into 0. So no solution from this factor. But this factor does generate a solution. So we'll set that equal to 0. And solving, we'll move the minus 1 across. Divide both sides by 3. Now I see a minus 2x here. So that puts it on the bottom. Now the numerators are the same, so the denominators must also be the same. So e to the 2x equals 3. Now we do a little trick here. It's called take the ln of both sides. The natural logarithm of both sides. And when you take the ln of both sides, the left side becomes 2x. Because the exponent you put on e to get e to the 2x is 2x. So that's what a natural log is. It's the exponent you put on e. So the exponent you put on e here is 2x, and on the right side it'll be ln 3. And of course now we'll divide through by 2, and we have our critical number. Evaluating our function at the critical number and the boundaries is all that's left to do. So f of 0, we'll start with this right here, f of 0, plugging in 0, do it yourself. F of ln 3 over 2. Now you can turn this into a decimal and plug it in here and use a calculator, and I suggest you hit the space bar and do that. F of ln 3 over 2 is that number. And f of 10, Similarly, subbing in 10 there, I got 0.quadrill05. And we can see clearly here that that's the minimum, and f of ln 3 over 2 is the maximum. So we used the algorithm and we found the absolute max and min. There's a b portion. X is in the interval from -4 to 4. Whoops. X is in the interval from -4 to 4. That's what this is saying. And the square brackets just means that -4 is included in the interval. So we'll take our function and we'll do the same thing. We'll have to differentiate it. So here I am differentiating this. First thing prime times the second thing. So that'll be 1 times e to the -2x plus the second thing primed. Now the second thing primed is e to the -2x times -2 times the first thing. Expanding it, so I multiplied this out to get -2x e to the -2x, and multiplying this I got -4 e to the -2x. And I see some like terms here, which they could be collected. And we have these two negative terms. -3 e to the -2x, subtract 2x e to the -2x. And similarly, we'll set this equal to 0 and factor. Here I've set it equal to 0 and begun the process of factoring. No, I completely factored it. So take out e to the -2x with a minus sign. Now it's a little bit tricky. But if you take out a negative sign out of both terms and an e to the -2x out of both terms, you can see both are negative and both have an e to the -2x. Common factor that out, and we're left with a 3 and a plus and a 2x. So x from this factor is equal to -3 over 2, and that's our critical number. So evaluating at the boundaries and the critical points, the critical numbers. F of -4, plugging in -4 to the original function. Hit the space bar and do it yourself, and you'll find that that's -5962. -3/2, so f of -3/2, I got 10 when I plugged it in here and used my calculator. And f of 4, I got 0.002. So very clearly there's the min, that's the lowest number, and there's the max. That's using the algorithm. Now the toughest part in this entire thing, I think, is this area where we're trying to solve for x, and that's what this video is mostly about. Moving on. Question 6. A rumor spreads through a population in such a way that t hours after the rumor starts, the percent of people involved in passing it on is given by a function. Percentage t of t is equal to 100 times the bracket e to the -t subtract e to the -4t. What is the highest percentage of people involved in spreading the rumor in the first 3 hours? And when does this occur? So we're doing a max-min problem. So the solution is to do the algorithm, actually. Find the derivative, set the derivative equal to 0, and evaluate. So we'll have to differentiate. There's our function, now differentiating. That's a factor, a constant factor comes along for the ride. Differentiate the terms inside this bracket. E to the -t differentiated is -e to the -t. That -4, when multiplied by this term, becomes positive when you multiply it by that negative. So it's positive 4e to the -4t. That's differentiating. That's from us earlier in the unit. Setting it equal to 0. I set it equal to 0, and I also common factored out e to the -t. So here's e to the -t is in both of these, so I took it outside the bracket, common factored it out, divided it out, and so that left behind -1 plus 4e to the -3t. And you can check by multiplying it back in. If I multiplied it in, I'd have -e to the -t, looks good, and I would have plus 4e to the -4t, because when you multiply these powers of the same base, you keep the base and add the exponents. So now we have to set each factor equal to 0. Now 100 is never equal to 0. We can ignore that. E to the negative t is never ever 0. It doesn't matter what you sub in, e to that exponent cannot be 0. So we have to set this factor equal to 0 to find our critical number. Oh, I tidied it up first. I moved the -1 just across there. I like it this way. So we'll have to set this factor equal to 0. And when we do that, we'll drag the -1 across, and so we got 1. Divide both sides by 4. See the minus sign here? That's going to put that on the bottom. And now, because the numerators match, the denominators match. And we can say that e to the 3t equals 4. Here's the trick. Take ln of both sides. And ln of that left side is 3t. So t is ln 4 over 3. Now what was our question again? What is the highest percentage of people involved? So there's our critical number, and there's our boundary point, 3 hours and 0 hours. Let's just evaluate at the boundaries and the critical numbers. There's our function. P of 0 is equal to 0. Think about it. Put a 0 there, you got 1. Put a 0 there, you got 1. 1 minus 1 is 0 times 100. P of ln 4 over 3. Now, if you turn this into a decimal on a calculator and sub those numbers into here for t, you'll get 47.25%. And P of 3, well, again, sub in 3 for here, do the math, 4.98%. So it's very obvious that we conclude that the highest percent of people involved in the first 3 hours was here, the maximum, at the critical number, 47.25%. And when did that occur? 0.4621 hours. And when you multiply that by 60, it tells you how many minutes. It's 27 minutes and 44 seconds. One last question. A doozy. A colony of bacteria. What's the difference between a bacteria and a virus? Let the biology people work that one out. I think it's because a bacteria has got a life of its own. Anyway, a colony of bacteria in a culture grows at a rate given by a function, n of t, is equal to 2 to the t over 5, where n is the number of bacteria, t minutes from the beginning. The colony is allowed to grow for 60 minutes, at which time a drug is introduced to kill the bacteria. That would be an antibiotic. The number of bacteria killed is given by a function. K of t is equal to e to the t over 3, where k bacteria are killed at time t minutes. Determine the maximum number of bacteria present, the time at which this occurs, and the time it takes for the bacteria to be completely killed off or obliterated. So there's our functions. This is our growth. The bacteria multiply as living things do. This is our result of introducing a toxic agent that kills them. And we need to find the maximum that this reaches and the time that that happens and how long it takes for all the bacteria to be killed off. Solution. Consider the conditions after 60 minutes to be the beginning of the event. At this moment, 60 minutes after the beginning of the start of the whole experiment, the bacteria has been growing for 60 minutes. So the population at 60 is 2 to the t over 5, which was that function, which is 60 over 5, because it's 60 minutes, which is 2 to the 12, which is 4,096. So there's 4,096 bacteria when the antibiotic is introduced. And we'll call that time when the antibiotic is introduced 0 minutes, t equals 0. So recall the general formula for exponential functions from grade 11. Y equals a b to the x, where a is the initial conditions. So in other words, 4096 is going to be our A. This leads us to the function for the population of bacteria after the antibiotic is introduced. And this is the function. P of T, where T is the minutes after the antibiotic is introduced, is equal to AB to the X. Well, it's actually A, the initial conditions, 4096, times 2 to the T over 5, minus those that are killed. That's why you see this here. T is the time since the antibiotic was introduced. And so all we need to do is maximize this. And you know what that means. You differentiate, set the derivative equal to 0, and solve. Let's do that. Differentiate it, P prime, which means we copy a function times the ln of the base. That's why you see a ln 2 here, times the derivative upstairs here, which is times a fifth. That's why you see this factor here is times a fifth. The whole thing's over 5. Minus, make a copy times a third. Now to solve one of these things, we have to solve for t when we set it equal to 0. And, well, I don't like the fractions. They're awkward. So when I set this equal to 0, I'm allowed to multiply through by a constant number. And so I multiplied through by 15. 15 over 5, so with this term, which is all factors, is multiplied by 15, it's 15 over 5, which is 3. So it's 3 times 4,096, times the ln 2, times this factor. And 15 again times this, divided by 3, is 5. So it's minus 5 e to the t over 3. And so now there's no fraction. Notice there's 2 terms here on the right. See this negative term? We'll drag it across the equal sign. Now you can see that both sides have a t in them. The key to this whole video is to take ln both sides. Now we're going to take a ln of a product. Now we know from grade 12 advanced functions, when you take a ln of a product is the sum of logs. So this will be, when I take ln both sides, it will be ln 5 plus t over 3. Ln 5 plus the ln of e to the t over 3 is the exponent you put on e to get t over 3. That's t over 3. Plus ln 12,288 plus ln of ln 2 plus ln of this. Now it's ln of a power. Now you know from grade 12 advanced functions that t over 5, well, it's a portable exponent. It can be put out front, so it's t over 5 ln 2. Carrying this forward. Well, let's go back and have a look at this if you wanted to gaze on this for a moment. Took ln of both sides, ln of a product, sum of logs, ln of each factor, ln of ln 2, ln of this, which is t over 5 ln 2. Now we have to take this and solve it for t. I sorted the terms. I put the t terms on the left. That's a t term, goes on the left. That's a t term, it goes on the left. It's negative now. That's not a t term, so it goes on the right. Now once again, we've got the awkward fraction. So once again, I'm going to multiply through by 15. And 15 over 3 is 5, so this will be 5t, and 15 over 5 is 3. So that's why this says 5t minus 3t ln 2. And everything's times 15. 15 ln 12,288. 15 ln of ln 2. 15 ln 5. On the left side, we'll factor out the t, and divide the factor over. And you can see we've isolated t. Now we'll take a calculator and turn that into a number. It's 38.2 minutes, the time after the introduction of the agent when the maximum occurs. And the question is, how many bacteria were present at this time? That's the next question. How many bacteria were present? We'll have to go back to the function itself. and sub in that number. So I did. I subbed in 38.2 both every time I saw a T. Took my calculator, and I got 478,156 bacteria. Now answers may vary by 2 or 3 bacteria because people will round differently because of 38.2 was actually a rounding. Now the question is, how long before they're all gone? To find out how long it is before the entire colony is obliterated, we'll take the function and set that P of t equal to 0. There's our function, and set it equal to 0. Here we got the 2 terms, so drag the -1 across, and we're starting to learn that when you see t in an exponent like this, we'll take ln of both sides. So ln of the left is just t over 3. And ln of the right is, well, it's a product, so it'll be the sum of lns. Ln 4096 plus ln of 2 to the t over 5. The t over 5 goes out in front, so it's t over 5 ln 2. I multiplied through by 15 again. 15 over 3 is 5t. 15 ln 4096. 15 over 5 is 3t ln 2. So I multiplied through by 15 to clear away those fractions. And this leads to, well, let's sort the terms. Put the t terms on the left. Let's common factor out the t. Take it out of both of these 2 terms. Take that factor and put it underneath and take a calculator. Calculator says 42.72 minutes.